All right. So, welcome back. How was your break?
It was great.
Amazing.
Good?
I didn't want to come back.
Too quick?
Yes.
You know what makes me mad? So my wife's on break this week, right? Because you always take spring break around Easter. They started their break Friday. So they get Friday and a whole week.
Yeah, no,
And
that
we only
makes
got a whole
sense.
week. Well, I know because Good Friday, right? But they had to wait longer for their break. So we would have had to wait longer
But
if we
still,
did
that makes
that.
sense. I get like Easter and plus. Because like.
Well, we got plus and then Easter.
I like Easter and then.
So it depends on if you wanted a vacation before Easter or after Easter.
I want it
All right.
after Easter.
So, hopefully everybody had a wonderful break and you're rejuvenated for the sprint to the finish. If you look at the calendar, we really have like a month of school left. That's it. So you have a month to survive and we have a week of travel. So, yeah.
Didn't we technically get like less than? Didn't we only get like 4 days on our spring break because everyone had Friday off? So
Everybody having it off doesn't stop you from having
I
it
know
off.
it doesn't stop us from having it, but
So
like,
then
we
think
could've
about the
had
question
day
that you're
off.
asking. How many days were you not in school that you could have?
4 or 5, but I mean,
5.
I don't know. I was kind of theorizing that it's like everyone would have had it off. So I mean,
So we got
It's kinda
5, they got 6.
Yeah.
We're going to
they
compare.
got an extra.
So it's not that we didn't get
They
Friday.
got an extra day.
Yes.
That's what I'm saying.
Alright, who can remind me, or remind all of us, what scientific notation is, and what the purpose, and like what the heck is this nonsense? Yeah, Jeremiah?
Okay, shrinking a like big number like 2 billion to something easy like 2 to the 10 to something to like
Not to the
billion
10.
times.
Be
2
careful.
times 10 to the something.
Now, why are we
That just makes
using
it
times
easier.
10 to the something?
So each of those zeros represents like thousands of a place, I think. Yeah, they. No, I don't.
Now, be careful. You're getting a little tripped up on your verbiage. Julian?
10 is easy to multiply.
N is easy to multiply by with, and our number system is base what? Base 10. All of our place values are operating on tens, hundreds, thousands. It all comes back to 10. So the reason that we use the times 10 to the power is so that we can represent really, really big numbers or really, really small numbers. So today we're going to dive into how we use that to represent really, really big values. So on the example slide up here on the start slide, notice we have 2 times 10 to the 9th. That first number has to be a number between 1 and 9.9999999. It cannot be 10. It has to be 1 digit before the decimal point.
Can it be
They
1?
don't have the decimal point, but there is a decimal point right after the 2. Can it what?
Can it be 1?
It can be 1, but it cannot be less than 1. So it has to have a digit in front of the decimal place. 0 is not a digit, it's just a placeholder. Right? So 0 is nothing. That does not count. You have to have a number before the decimal place. Or the decimal point. So that then, ironically, that you had said 2 billion, I don't know if you looked at this and thought about that, but that's representing 2 billion. Now, here's the dangerous thing. Oftentimes when I show an example like that, people say, oh, there's 9 zeros. That's why the power is 9. Kind of. Because that could also be 2.846 times 10 to the 9th. And if I do that, are there going to be 9 zeros?
No.
No. I'm going to move my decimal point 9 places, but that would end up giving me the number.
Why could you say that as 2.846 billion?
You could, but if we're going to write it out in standard notation, this is our standard notation. Now when you say it, you can say it however you want, but we're talking about how we write numbers, how we represent them. So yeah, you're fine. If you want to say 2.846 billion, but normally if there's more than 1 digit after, they'll say like 2,846,000,000. That'd be a lot to say 2.846. It's kind of excessive. So be careful. The power is not how many zeros you have. It can be, but it is not necessarily. So check this out. 384,000. If we want to represent that in scientific notation, if you start with the big number, then think about how do I write that number as only a digit, then a decimal point. So off to the side here, I want you guys to make like a line, a big fat decimal point. We'll go a couple more lines. So what you have to determine is, well, what's my first number? Well, and I really said that wrong. You don't have to determine that. You just have to rewrite what you've been given. So, what are the numbers that we have? 384, and then some zeros, which we don't care about the zeros. So we're going to use 384, and you just drop that decimal right after the first number. Now what you have to figure out is how far will this have to move to go back to the original value. So how do I get to the number that I started with? Well, I move this decimal place, or decimal point, how many places?
2.
To get to the original 384,000?
Oh no, 5.
So if I move it 2, I get to the end of my numbers, but that doesn't get me back to my original number. I then have to move 3 more, and these all turn into zeros. But once the decimal lands out there, that gives me the power of 5 because I had to move 5 places. And because we went to the right, it stays positive. Now the next lesson, which we might get to today, is if I need to move my decimal the other direction, the only thing that happens is the power is negative instead of positive. Remember when we talked about powers and exponents, a negative power is putting that 1 over, and we'll get to that next lesson, I'm kind of going too far. But does this make sense, that this 5, the power of 10, tells you how many places we move the decimal?
Yep.
Any questions? Wunderbar. So, if we means wonderful in German. Which, and actually, I think it is a candy bar. Like, I think there is a Wunderbar, which is just a wonderful candy bar.
we have a whatchamacallit.
We do have a whatchamacallit. I like Toblerones, whatever those are, because they're a triangular prism, kind of. But then each one is a pyramid. The box is a prism and the candy is a pyramid. So, now the other method is if you start in scientific notation and have to work to the original. So, we look here, and this 6 tells us move 6 places. And we can go ahead and say right, because there is an option to move left. So that tells me move 6 places right. And really, I just start counting. So here's my method. Give me your eyes for a second. I know that I have the number 732. And I know that the 7 doesn't count as a move, right? Because the decimal was already here. So then I just start counting. I need 6. So I go 1, 2, 3, 4, 5, 6. That. Except my brain wrote the 6 instead of writing another 0. So then I place my decimal point, and I place my commas, and I figure out what this number actually is. 7,320,000. Or 7.32 million if you felt like it. You can, if you want, put another 0 out here just for accuracy's sake. You do not need to. This 0 doesn't tell you anything except for that there are no tenths. So some people like to put that 0 because it makes it obvious, hey, here's my decimal. I am now, like, these are tenths, hundredths, whatever. And there's none of them. Any questions here? So now we get to drop lots of real knowledge on you.
Yeah, real knowledge. I
In
love real
astronomical units, and this is funny when people say, like, oh, well, that's an astronomical amount. We literally have the astronomical unit. And the astronomical unit is approximately 93 million miles. Because that, use your reading powers, is what?
really far.
Aside from really far.
Between the distance of the Earth and the sun.
Sun, us, 93 million miles. If you've ever wanted to feel really small, go run a mile, and then look up at the sun, and realize that that is 93 million times as far away as what you just ran. So, that is how we gauge things in space, right? Because if we just use miles, guys, we're going to be representing things with giant numbers. Because if that's the distance between the sun and the Earth, what do you think about the sun to Pluto or Jupiter or Saturn or any of those further out planets? Or our not planet or our debatable planet?
Dwarf planet.
Pluto.
Pluto, right? Now that's sad because in my mind, Pluto's a planet.
Why can't Pluto not be?
There's this debate of whether he counts as a planet or not. Just look it up. We don't have time to talk about it right now, but look it up.
It's a dwarf planet.
Just look it up. We'll, maybe after testing, we'll go deep into this project.
It's the rules of being.
So, we want to express this 93 million miles in scientific notation. So what digits, what numbers do I actually need to represent?
9.
The 9
The 3.
and the 3. So start by saying, okay, I need 9.3. Those are the numbers that I need to represent.
And then million.
Times 10 to the, and then we'll figure out our power. Now, if you can't figure out your power by just like number sense, write out the original number. My original number, 93 million, will be that. So you can just then ask yourself to go from,
Yeah, I was right. 6.
to go from where I've now put the decimal to where the decimal actually needs to be. What's that distance? How many places?
7.
1, 2, 3, 4, 5, 6, 7. That tells me my power must be 7. And that will then equal 93 million miles. That will get my decimal point back to where we actually want it to be. But this is a lot quicker to write and do math with. It's just 9.3 times 10 to the 7th. And actually in your calculator, sometimes if you ever see this pop up, if it says 9.3e7, that means the same thing. That means the exponent power of 10 is 7. It's a weird shorthand notation, but if your calculator ever throws an e in there, that e represents times 10 to the.
When do you know when it's this?
Well, so what it's doing is it's using less of your screen. So if it was trying to show you a really big number in scientific notation, say it was trying to show 9.3684127 times 10 to the 16th, the screen might not be able to fit that. So instead of using 3 places for times 10, they just put e, and it uses only 1 place. Like, you know what I mean? Like 1 letter place as opposed to the times, the 1, and the 0.
When do you know if it's this E or the other E?
The lowercase. The other one's lowercase.
Okay.
Yeah, so big E. I don't think these yellow calculators do that unless you have it in a certain. You can play with it. It would be what mode it's in. So if you figure out how to make it spit out a number like that, tell us what mode it's in.
Alphabetical, which is the same.
Well, so when you go into the mode here, if you guys haven't played with this, I would love it if you'd grab one if you're not comfortable with mode switching on this. Mode is this button right up under your screen. Right, so you hit mode, you're going to have options. You have deg, rad, grad first, which means degrees, radians, and I forget what GRAD means, but leave it in degrees. You can either put it in normal or scientific, so either norm or sci. And then your float, right below that, is how far will it let your decimal places go? What do you think float means?
It stops.
That means
Because like what ours does, it goes like 0.333333334.
Yeah, well if something is floating, are you controlling it? No. So float just lets it do whatever it wants to do. If you change your settings, I'm trying to load up presenter, but I don't know if it's going to come up. If you change your settings and change that float to a 0 or a 1 or a 2 or a 3, that's how many decimal place values it will let you have. So, if you, let's say we put it on to 2.
Oh.
Do a third and then just hit enter. So 1 divided by 3. It stops me at 2 decimal places. If I instead tell it to float and I go do the same thing, it floats it out as many decimal places as it can show. But now if I start trying to represent really, really big numbers, like if I type a bunch of 5s times a bunch of 5s, I don't know, whatever, it's going to give me my value in scientific notation using the times 10 to the power.
Cool.
Now, and I don't know if I can get it on here, if we switch it to classic, it might then, nope, it still shows times 10 to the 12. So I think these calculators will always show you times 10 to the. But if I did that, let's see if on my TI, this is actually really bright, so you guys, no, maybe one of these. So So this is the TI-83, the graphing calculators. If we did the same thing, I don't know how many 5s I typed, but a bunch of 5s times a bunch of 5s. See the E?
Oh yeah.
So that's where it changes. So between this calculator and these are different.
Is it
Hey, I got the exact same number.
That one
I
has
typed the same amount of 5s.
that one has a really big screen, so like why is it?
Well,
why
it's
is it
not
big?
any wider. It's only taller.
I know,
It's-
but look,
no,
with the
that's
5s
big.
it went down. With our calculator, it like just goes dot dot dot, and yours went down. So couldn't that it just do that with that
And
answer?
then
Yeah, but it wouldn't. You don't like to split answers up. So if you can keep it on the same line, it would prefer to do that. So there might actually be numbers beyond that 3. But what we say, and sorry, these aren't the same exact values. That's to the 21st, and this is to the 20th. But we would just say that those are non-significant values, and we just don't have to represent those. So if I was going to represent this in an abbreviated scientific notation, I would probably only write 3.086 times 10 to the 20th, because we're rounding. Now, we don't always. Sometimes we want the as precise as possible. But like, my brother-in-law is an accountant for hospitals, and they round to, like, they don't deal with pennies at all. Like, they don't deal with change at all. So by the end of the year, based on rounding, they end up with errors around $1 million, which is acceptable. That's acceptable error range because it's due to rounding. And that's okay. Because they are doing hundreds of millions of dollars throughout the year. So if you think of every transaction, maybe 15, 20, 30 cents off, over time that adds up to a lot. So we talk about significant versus non-significant values. Light, if you want to talk about light speed, it travels at 186,000 miles a second. Not per hour, per second. So when you're watching those movies or whatever and they say, all right, light speed, you're going 186,000 miles a second.
That's one.
You know what? I don't like this question. We're going to change this question. Because we're used to speed in miles per hour, right?
Oh.
So if we wanted to talk about this in miles per hour,
You have to times this
Multiply it by 60.
so multiplying by
and then
60 would give you miles per
And then
minute.
multiply by 60 again.
So what if we multiply this by 60, then times 60, which really would be times 360? What do we get as our speed?
I don't know.
6, 6, 9,
Just like
6, 0, 0, 0.
Hold on. 6, 6, 9.
6, 0, 0, 0, 0, 0.
Confirm.
Yeah.
So this is one of those situations where you're deciding how many digits are significant. Can I represent the 6696 pretty easily? Just 6.66, or yeah. So I could say 6.696, or I could round, and if I wanted to round, well, the 6 tells the 9 to go up, the 9 tells the 6 to go up. I could just round this to approximately 6.7 if you wanted to, if you were trying to be really shorthand, but then we still need our times 10 too, though. How far does this decimal point have to move to get back to where it actually started?
I only got 4 zeros.
Yeah, I did too. I wasn't gonna speak up.
Yeah, it's
Why
got
not?
4 zeros.
We have one extra 0. I gotta move all my commas
Yeah,
in.
it's 4 zeros.
And it's 7.
Sorry, calculator's hard to keep track of. Like how many zeros?
Yeah.
6, 0, 0, 0, 0. And what's fun about this is it doesn't change what I've already written, the 6.696. I'm still fine to have that, because those are still my start digits. But what I have to figure out is to go from where I placed it to where it actually belongs. How far is that?
7.
1, 2, 7 digits.
Yeah, my comma's in the wrong place. My comma belongs here. Sorry, this comma should disappear, but I can't erase it now. So that is going to be 7 places, and whether you use it precise or whether you do it rounded, still times 10 to the 7. Now, change your label though. We want to make sure that we put miles per hour.
What is it?
Yeah.
It's always an hour, or you can just put 1.86.
You could use this speed, but I just wanted you guys to understand what it actually is in miles per hour. So if we compare that to like the fastest car there is, most cars, well, sports cars, max out about 230 miles per hour, which is really dangerously fast. We're talking 66,960,000 miles in 1 hour.
You can fly at that speed.
Now, even flying as fast as we can right now,
It's only like 600 miles per hour.
it takes months to get to Mars. Like over a year, I'm pretty sure. That's how big space is. So when we're talking about scientific notation, the main reason we use scientific notation for big numbers is space. We don't really have numbers that astronomical, which means literally space, but also means like really big. We don't have numbers that crazy big on Earth. What we have on Earth is numbers crazy small. And we'll get to that in this next one. Express this in standard notation. If this is the approximate age of the universe, or we're talking about how big space actually is, what is that in actual standard notation? Now, age of the universe, this is going all the way back to, and I'm not getting in any kind of religious debate or anything today, Big Bang. So whether you believe in it or not, Big Bang created everything. And there are plenty of religious ways where you can say, yeah, the Big Bang happened, and then also creationism happened, so don't worry, there's a blend. But this is back to the Big Bang. How old is the universe? The oldest particles that we can observe based on carbon dating or whatever. Mom, so what do you got?
13,700,000,000.
13, comma, 700, comma. Now, I like to write all my digits out before I ever place a comma. I trust Masa a lot, so I went ahead and placed them. Well, let's check. 3, 6, 9, 10 spaces. So from where it was, it moved 10 places to get here. And that would be years. When I'm writing it, I don't place any commas until I've placed my decimal. Because you'll just end up having to erase that. Any questions?
No.
It's so old.
It is so old. And then you think about your time span here, maybe we'll get 100 years. Think about the blip
That's very
in
unlikely.
history.
What's a
Like blip is just very small, like a tiny little thing. So like when you think about like, oh, this is the end of the world, everything's really kind of microscopic when you think about it in the big sense. Julia?
Oh crap, I forgot what I was going to say.
It's alright, so did I. The moon, if you want to talk about closer distances in
Yeah,
space,
I like the moon.
is that far away from Earth.
Okay.
How far is that in standard notation? You already have it, Sean?
No.
Did you have a question?
Yeah, but because back on the Goddard, when we're converting the seconds to an hour, when you do 60 times 60, that's 3,600.
Yeah, sorry, what did I said 360.
Yeah,
So is that wrong or is that right? The one up, sorry, the one above it.
that was wrong. It's supposed to
With a 4, did we need 4 zeros or 5 zeros?
be 5. So Ellie was right.
That's because she did it right instead of listening to me. So I do occasionally make mistakes. You know, like one per day or something like that.
I don't
So go back in your notes real quick. I don't even know what to do actually. Let's put a star here. And there's actually another 0, which means that this is going to have to move another place value, so that will actually be 8
What?
instead of the 7.
What?
Oh, that looks weird.
So this is the problem. Anybody who did times 60 times 60 got the right answer, but if you listen to me when I went too quickly and did simple math wrong in my head, hey guys, don't always trust what you do in your head. 60 times 60 was 3,600. I misspoke and said 360. So if you listen to me, your power's off. Just make sure you understand how to use scientific notation and don't blindly trust me.
Listen to us.
Okay.
Trust me, but don't blindly trust me. Check on my info. Julie?
Should our lifespan increase as we get like older?
It depends. Like, you can argue that as science progresses and everything else, but the other side of it too is what's going on with our planet and our environment.
It's
So even if our lifespan is increasing, if there's more
Bad stuff
cancerous
in the air.
toxins in the air, all the advances in science won't help me if we have a 3 times higher cancer rate than we used to. You know what I like? So there's kind of debate on both sides of it. Anish,
Got it.
you got this?
Yep, 240,000.
What'd you say?
240,000.
So 240,000.
Confirmed.
So that, guys, is somewhat manageable, right? 240,000. I've traveled on a vacation like over 1,000 miles driving. So, you know, compare driving 1,000 miles to, let's drive to the moon. That will only take 240 times that. And to go 1,000 miles, it takes you like a day. Yeah, a long time.
So like almost
That would only
like
take
2/3 of a year.
So if you're driving 1,000 miles, and let's assume a speed limit of 65 miles an hour. Yes, my battery's critically low. Thank you, I know.
What percentage?
It takes you 15 hours of constant driving to drive 1,000 miles. Driving at highway speeds. So, if you imagine if you could drive to the moon at a, let's even go Kentucky, well actually the freeway speeds of 70. We'll let you go a little bit faster. You're going 70 miles an hour. How many days, just guess, how many days do you think it would take you to drive to the moon?
270.
3 years.
270, 3
1 million.
2.
5 years.
6 years.
142.
Oh.
Years?
142 days.
Oh,
The moon's not that far.
almost.
The moon is close. In the grand scheme of space, the moon is close. So, if you could drive a car, or if there was a space shuttle that drove the same as a car, and you drove at 70 miles an hour, take you 142 days.
But you wouldn't even.
Now, let's say if you were driving some sports space shuttle, and you could go 250 miles an hour. There are cars that go 250 miles an hour.
Like the new Lamborghini that's
That would only take you 40 days. Take you just over a month. You could drive to the moon in a month. Like Elon Musk and those guys are looking at ways that you could literally vacation into space. Try. Oh, so this is pretty obvious. Who can give me some values that you think would be crazy big, not related to space? Because all we talked about today is space. Huh?
6 quadrillion.
But what would that represent? Give me like real world application, things that you think.
The distance between the atoms.
So I'll come back to you. Ozzy?
100.7 billion. Yeah, 100.7 billion.
But what would that relate to?
I don't know.
Don't just throw numbers at me. We want to talk about what it could be. Anish?
The nucleus to the electron.
What?
That's what I was about to say.
In the atom, there's a nucleus and an electron.
Okay. So what about it?
So it's like, I don't know how many.
We did this.
How many of one thing are inside of another thing?
Yeah.
Jeremiah?
There's
Come
like
on.
14 billion ants on Earth.
Yeah, like how many ants are on the Earth?
Like the human population.
Yeah, we're in the
7.5 billion.
Yeah,
Like
so you could, like, billion is right around that cut point where people could write it out. Like, you could write out a billion pretty easy, and 7 billion, whatever. But once you get bigger than that, you don't really want to represent that. So we do sometimes represent that in scientific notation.
We're like 7.4 billion.
What about skin cells on your body?
That's a lot.
What about possible hairs on your body? Do you know we can actually, and this is some scientific notation math, take the population of the world. Now, I'm going to blow your mind here for a second. Take the population of the world. Jeremiah, chill for a second. I'd like to blow your mind. Take the population of the world and the largest possible amount of hairs that you can put on your body. We did this in college. It was a really fun math problem. So, scientific notation, right? How many possible hairs could be on your body if, like, everything... So we looked at how many hairs are in a square inch. Like, literally, how many hair follicles do you have in a square inch? What's the surface area of the human body? And we compared, like, average, of course. We compared how many humans versus how many hairs. There is mathematical proof. Well, and this won't work for every single person, but you can prove that there is somebody else on Earth with the exact same amount of hairs that you have on your body. There's somebody else on Earth with the exact number of hairs. And we prove that through some math.
If you
Then
pluck
there's still
one, then there's
somebody
else.
Now you're matched up with somebody else. Or maybe that one person, they lost a hair when you plucked one. Because you're constantly getting new hairs and losing old hairs. So that's a fun math application using those really big numbers. So let's try this. What about when we compare populations? And we did that through a comparison method of comparing hairs to humans. But now let's compare bacteria populations. So if we have 79,854,000, let's write that in simple scientific notation. Let's make all of these have just digit, decimal, digit, digit. At most, you're going to write 3 digits. So for A, we're going to go ahead and just round that to 7.98.
8, 9.
100,000.
9.
7.99.
This 8 is going to get rounded up by the 5. So if we want to represent this only using 3 digits, it'd be 7.99 times 10 to the, how far, anybody? 7th. Try the next 3 on your own. Take a second. Write them all using only 3 digits to represent it. Then try to answer those true-false questions.
And what are we rounding to?
3 digits.
So in your scientific notation, like the value at the beginning, the base, that's what we call it in the scientific notation. Our base values we rounded to 3 digits or 2 decimal places. So, unless I made a mistake, which I could have, we had 7.99 times 10 to the 7th for the first. Then we'd have 2.12 times 10 to the 6th. 6.18 times 10 to the 6th. And 3.97 times 10 to the 5th. Now this gets difficult. So now, Dom, when question A asks colony A has about 40 times as many bacteria as colony B, do you think that's true or false?
I said false.
Why'd you say false?
Because I did colony B times 40. Different number. Oh wait.
Notice they said about. So let's break this up. Let's make our life easy.
About, yeah.
Looking at the starting values, the bases, about 2 compared to about 8. What would this be to go from base to base? Dom? Approximately 4, right? Around 4. Then 10 to the 6th compared to 10 to the 7th. What's the difference between 10 to the 6th and 10 to the 7th? 1 value of, 1 power of 10, right? So this is a difference of 10 to the 1st. So if that's times 4, and this is times 10, then this is true. Because there's a times 4 and a times 10. So that's where this gets easier to work with. We can also set this up using the actual division method. So colony C has about 30 times as many bacteria as colony B. I want you on your paper, please, to take colony C, 6.18 times 10 to the 6th. Colony B, 2.12 times 10 to the 6th. If I just look at the base values, compare those with each other. How do they compare approximately?
About
3.
About 3 or a third, right? So about, my numerator's 3 times bigger than my denominator. Then times 10 to the, well, if I look at my tens, my powers, how do those compare?
they're
what happens when you have a number divided by
Cancel
itself?
out.
1.
So this becomes times 10 to the
First.
0.
10 to the 0, because remember, this is actually 1. So be careful, the difference between these, the multiplication, is just times 3, not times 30. This is false. And you could have compared right here and saw that as well.
But I thought when the 8 when the 8 is divided by 2, just basically just subtract. So why is there a 0
What are you talking about?
for when the it's next to the 1 divided by the 8?
You're talking about 6.18 and 2.12?
Yeah, shouldn't the 8
Imagine this as 6.2, let's round this, and 2.1. Or just 6 and just 2, if we really round it. You're not dividing each number, you're dividing the 6.18 divided by the 2.12, which is about 3. Yeah, so don't do each individual. But then these are the same numbers and they just make 1. Because 10 to the 6 divided by 10 to the 6. And question C here. Colony B has about 5 times as much bacteria as colony D.
That I put true because I realized colony B, so colony D, 397,000. If you multiply that by 5, it's just on the brink of hitting 2 million, whereas B has 2,124,000.
Yeah.
So that would be true.
So check this out. I hate that I cleared all of my ink. But if I look at D, 3.97 times 10 to the 5th we had, and I try to do that times 5, what do I multiply by 5?
The whole sum of all.
If I did this value, 397,000 times 5, I just take the 397,000 times 5, right? So I just take the number times 5, but now my number's broken up into 2 pieces. This is decimal shifting. This is the value. This is just decimal shifting. This is the actual numerical value. So when we do this, we just take the 3.97 times 5 and figure out what our new base would be, which that's approximately 4. So if I do 4 times 5, what do I get?
Around 20.
20, and now I get 20 times 10 to the 5th. Well, snap. That's not scientific notation. Because this 20,
above 10.
this is written using a power of 10, but it's not
So,
scientific notation.
2 times 10 to the power of the 6.
So 2 times 10 to the 6th, which is approximately what we had here. We had 2.12 times 10 to the 6th. So this comes out to be true. Approximately. Notice we're using the word about. About lets us do approximate math and round. Sorry, I should have captured that. Let's get your next notes passed out. We might dabble in this a tiny bit today, but your homework will only cover 21. I know, that one's the same thing that we just did. Try, while I pass this out, do the got it on your own. We'll review that really quick. It's the same thing we just did. Pass these back, please. Spread these guys out if you would.
Oh, yes.
Pass these back, please. I'm sure you can guess what today. So it says, the number of bacteria in colony A is how many more times colony B? If A is bigger than B, how do I want to set up the division? A over B or B over A? A over B, it's easier to have bigger number on top. So if you set up 4 times 10 to the 6th over 2 times 10 to the 5th, what moon did you get? So let's break this up. What's 4 divided by 2?
2.
So first, we get a 2. Then, what is 10 to the 6th divided by 10 to the 5th?
Well, the 10s cancel out.
Careful. Because this 10 to the 6th is really telling me 1,000,000. And this 10 to the 5th is really telling me 100,000. So they don't cancel per se. Some of their parts cancel, but we're
Tens cancel out.
kind of. What do we do? Do you remember our work with exponents? If we have the same base, and then the exponents dividing, what do we do with those exponents when we divide?
Subtract.
We actually subtract. So this becomes times 10 to the first, 6 minus 5. So when we do the division, guys, this is why I wanted to go over this, because I'm sure over spring break you didn't work with exponents. So when we divide with exponents, we actually subtract. So this becomes 2 times 10 to the first, which 2 times 10 to the first, well, 10 to the first is 10. 2 times 10. So colony A is about 20 times colony B.
It's pretty big.
Oh, I don't
That's
know.
what I did. I just guessed that.
Questions, comments, concerns? Oh, by the way, this is a fun fact for my spring break. DJ Hudcap is actually legit now. I got paid for a job.
How much?
I didn't expect it, but my brother handed me a check. I DJ'd my brother's wedding. But yeah, so then he handed me a check, and I was like, okay.
Just like a YouTube channel. It's got the Abbreviated.
They give you $1,000 out of nowhere.
No.
No, not $1,000.
Not out of nowhere.
1,001.
No, 1,000 to the exponent.
So, now on the flip side of things. What if I asked you to measure in miles how wide your hair is? Like a hair.
Is it like 0.0?
I represented it in 10 to the negative something.
What if I asked you in inches? Or maybe even centimeters? You're getting closer.
If I hear
Hold on. So I have a question that I'm really getting to. Will we have a whole unit?
Maybe.
No. Well, even if we go to centimeters, guys, a centimeter, you might be thinking millimeters, but a centimeter's that wide. Your hair is not that wide. A single hair, for those of you playing at home, is not going to be this wide. So we're not going to have a whole unit. We just won't.
Of course it is.
So when we do not have whole units to represent values, when we have only partial units, and even then, very, very small amounts. So we start with this number, and I hate that they show the decimal in both places. Go ahead and write here, this is our start value. I hate that they show the decimal in both places. So they start by representing, I forget what this shows, it might just be a number that they made up. But this is a very small quantity, 0.000234. So to represent it using tangible values, we change and we use the first numbers that matter. These zeros don't really matter except for where the decimal is, but we don't need to write the zeros. So we just start writing 2.34. Then we gotta tell it what to do. Well, to get back to the original, you gotta really multiply by 10th, 100,000, 1/10,000th. So, or this fraction would be 1/10,000. Actually, off to the side, let's go ahead and put this is 1/10,000. 10ths, 100,000ths, yeah. Which I could really represent as 1 over 10 to the,
Something.
how many?
10 to the.
Not negative yet.
to the
10,000. What is
10 to the
10,000?
Yeah, 'cause it's in the
10 to the 4th.
Oh.
So think about it. If my decimal was, like, how many times would I multiply 10 to get 10,000? 10 times 10 times 10 times 10. There's 4 of them. This turns into this. That's how that happens. So I like to show the in-between. They jump straight from decimal to the power of 10. Well, why does that happen? Is the fact that this 1/10,000th can really be represented as 1 over 10 to the 4th. And when I go to use not a fraction, but just the power of 10, I have to make that negative because this communicates that it's really 1 over 10 to the 4th. So these are the same numbers, just one uses positive powers, one uses negatives, and some of you guys had issues on your mastery with that. I would have those ready to get back to you, but I had to go take care of a couple things this morning. I will have those for you tomorrow. They're graded, but they're not in the grade book. So we're out of time for today. So tomorrow we will pick up right here. You just had a little taste of the tiny values. Your homework tonight should be all ginormous values. Thank you guys. Have a wonderful day.
You too.
Thank you.